Oh, wow. Thank you so much for letting me know. Oh gosh, that was horrible of me. So, general relativity. So, um, what Newton felt about gravity was that it was a force, an invisible force that permeated all space. It was like this invisible spring that connected different objects, and that this force acted instantaneously. And he gave this famous equation that you've been aware of. The force between two objects is proportional to the product of their masses divided by the distance between those masses squared. Okay. Albert Einstein had a different view, and his view is the more correct view, and that's gravity is not a force. Gravity is caused by the deformation of spacetime. And here's his equation. This equation looks deceptively simple, but this is the most complex and difficult to process equation in all of physics. So basically, the way to translate this equation into words is that matter tells space-time how to warp, and space-time tells objects how to move. Okay. So to Einstein, gravity isn't a force. Gravity is a warping of the fabric of space and time itself. And particles just traveled their natural path on this warped space-time. So this is review. Remember, the special theory of relativity is all about movement, and that what they say is that time and space vary depending on your velocity. General relativity is all about gravity. And one of the great postulates is that gravity and acceleration are one and the same thing. And gravity is a distortion of space-time by mass. And it predicts that everything will follow this distortion, not just particles, but light and neutrinos and everything else. So this is a common representation of space-time. Um, and the common representation of space-time is, instead of living in a three-dimensional universe, pretend that we live in a two-dimensional universe. And this massive object in the center warps this two-dimensional fabric of space-time, and then particles don't have to do anything special to roll around this depressed ball. And you'll see a demonstration of that. In fact, I think you saw that last time. So here again is this two-dimensional representation. Again, this is an analogy. This isn't real. This is because, again, we're showing space-time as two-dimensional, not three-dimensional, which it really is. And the paths that the planets follow are the paths of least resistance. You're just rolling around like pennies in one of those things we used to see in malls, where you roll a penny around and it goes woo, 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 woo.
To look at the body's influence on the space they're embedded in.
And here's a three-dimensional
So in Einstein's
representation.
picture, a massive body makes a depression in the space-time around it, so that other bodies following their natural paths tend to be attracted to this depression.
Okay. And so we've talked about that last time, but here I want to talk a little bit more. This depression in space-time creates this dimple that particles fall into, and particles will orbit around. And so it's a kind of a natural analogy. So what's a black hole? A black hole is literally where that warping of space-time becomes infinite. And in fact, you actually punch through space-time itself when you become a black hole. What I mean by warp through is not well defined. All we know is that what happens inside a black hole is outside any equations that we have. So what defines a black hole? A black hole is defined as where the escape velocity equals the speed of light. So for example, when I throw an object up, okay, it promptly comes down. If I throw that object up at 17,500 miles an hour, it will escape the Earth, because I have thrown it up at the escape velocity for the Earth. And every rocket that tries to put something in orbit or put something in interplanetary space must reach that speed of 17,500 miles an hour. That's the escape velocity of the Earth. Or I forget, was it 7 kilometers per second? I forget the exact conversion. Well, as the object becomes denser, or attains more mass, what happens is that escape velocity goes up and up. And as the escape velocity goes up and up, it becomes harder and harder for things to escape from it. And a black hole is where that escape velocity reaches 300,000 kilometers per second, as opposed to 7 kilometers per second. So we have a while to go before the Earth becomes a black hole. What this means is if light cannot escape the surface, then nothing can escape the surface, because nothing can travel faster than the speed of light, which means that by definition, no information can ever escape from inside a black hole. So, what happens inside a black hole stays inside the black hole. You can travel into a black hole, but you're never traveling out, and you're not even sending a letter home once you go in. So the definition of black hole is when you have material such as in a type 2 supernova core collapse, that material cannot withstand, none of the other three forces can withstand the force of gravity. It's so strong that the material collapses. And we don't know what it collapses to, but many people think it collapses into what's known as a singularity. A singularity is a single point in space-time that is infinitely small and infinitely dense. Again, we don't know for sure because we can never look inside a black hole, but there's nothing in our laws of physics that would prevent the collapse of matter into that singularity. What we can see is up to the event horizon, because the force of gravity becomes weaker and weaker the farther away we go. And the radius at which the escape velocity equals c, because it would be greater than c in here and less than c out here, is defined as the event horizon. And the event horizon radius is called the Schwarzschild radius. So the Schwarzschild radius defines the size of the black hole, and the event horizon defines this membrane that surrounds the black hole. Okay, there's the event horizon. Now, here is the escape velocity equation that you've seen previously. The escape velocity is equal to the square root of 2gm over r. So the escape velocity increases as the mass increases. The escape velocity increases also as the radius decreases. So if you want to increase your escape velocity, either increase your mass or decrease your radius, either way. Now, if we substitute c for the escape velocity and then flip this equation around, what we wind up with is the Schwarzschild radius, rs, is equal to 2gm over c squared. So this is just a very simple definition, okay? We're just using the equation for escape velocity and spinning it around. And it just so happens this is the correct equation, although we're not using any general relativistic parameters there, okay? So how do these form? Well, they form, we believe that what we call stellar mass black holes, smallish black holes that are just a few solar masses, form in type 2 or core collapse supernovas. And if you remember, we talked about degeneracy pressure, not in a lot of detail, but degeneracy pressure is what keeps a white dwarf from collapsing. And a degeneracy pressure, you've got a lot of material, typically carbon, that tries to compress because gravity is so strong. And the electrons don't like to be in the same place at the same time. And so they create this pressure that keeps the thing from collapsing. And that pressure is independent of temperature, unlike normal pressure, which is dependent on temperature. And that keeps white dwarfs alive. But that degeneracy pressure gives up the ghost when we reach 1.4 solar masses, the Chandrasekhar limit. And then what happens is the protons, the core collapses, and the protons and electrons combine to form neutrons. The neutrons all sit on top of each other, and the neutrons don't like to be in the same place at the same time. And so they create a neutron degeneracy pressure that is the basis for neutron stars. And that neutron degeneracy pressure gives up the ghost when we reach 2 to 3 solar masses. By the way, this is uncertain. We don't know exactly where it is. We do know it's between 2 and 3 solar masses. We don't know the exact number, unlike the Chandrasekhar number where we do. Part of the reason we don't know this exact number is we really don't have any way of measuring or monitoring neutron degeneracy pressure, because there's no way on Earth that we can create experiments to replicate those sorts of that sort of environment. And so when this neutron star reaches 2 to 3 solar masses, gravity wins against all odds, and the thing collapses to what we believe is a singularity. So we have white dwarfs, we have neutron stars, and then we have black holes, the three endpoints of stars. And again, here's the black hole, size of Chapel Hill. Its density is infinite. We believe there's a few million of these in the Milky Way galaxy. We've observed around 100 or so, I believe. And we know that they must be greater than about 2 to 3 solar masses. And they're created by stars that were very massive when they were born. And that's one of the reasons why there's so few of them, because there really aren't that many stars that massive. Characteristics of black holes. Well, we talked when we talked about relativity about time dilation. Special relativity says that time slows down when you're moving quickly. Okay, so when you see a rocket moving by you, you can observe that they are moving very slowly. And if they go off to Alpha Centauri and then come back, you would have aged 40 years, they would have aged 10 years. It would be very awkward meeting. Okay, and this is not just an appearance, this is an actual effect. Time slows down when you're moving quickly. General relativity says that time slows down when you're in a gravitational field. This is it's also a dilation of time, but it's with a different cause. So the closer, the stronger the gravitational field that you're in, the slower things seem to move. So if I'm in interplanetary space and I observe you approaching a very massive object, it looks like you are moving slower. Okay. So we have two time dilation effects that really have nothing to do with each other, but they're both part of relativity. One is part of special relativity, one is part of general relativity. How close does a star have to be to get to a black hole for it to be engulfed? Mary, hold that thought. I'll be talking about that, if not in this lecture, then next lecture, because that's an interesting topic. I actually went to the AAS meeting in March, well, virtually, of course. And they actually had some simulations about that exact topic. So there's the equation. Don't worry, you are not going to be responsible for these equations, don't worry. But I did want to show you these equations, that this time dilation depends on the velocity that you're moving relative to me. And this time dilation depends on how close you are. That's the Schwarzschild radius, how close you are to the Schwarzschild radius. Okay. So please enter your comments in chat. So if you are in the International Space Station, how does your time vary relative to the Earth? In particular, this was actually tested explicitly when they sent one of two identical twins, Kelly, I forget which one, went to space and the other one stayed at home, and they aged at different rates. But the question is, did the one in the ISS age slower or age faster? They age faster. 1 millisecond per year. So Art, yes, that's correct, but why? Their time passes more quickly from our perspective. So why would time pass more quickly from our perspective? Because several of you says they age faster. They are more distant from the massive body of Earth. Well, okay, so let's walk through this. They are they're moving very fast, right? So because they're moving very fast, from our point of view, would their time slow down or speed up? So remember, there's two different effects. So if they're farther away from us, are they slowing down? I'm sorry, if they're moving very fast relative to us, does their time appear to be slower or faster? Well, okay, so here's the thing. By special relativity, in fact, let's back up. By special relativity, their time slows down relative to us. Okay. And that's correct, Brody. It's different. And so for general relativity, does their time speed up or slow down relative to us? That's correct. So in terms of general relativity, they are farther away. And so they would seem that they would look and see that we are moving slower. And so since we're deeper, closer to the gravitational well, they would appear to speed up relative to us because they're farther away from the gravitational field. So in other words, for the ISS astronauts, we have two effects. One effect is that because they're moving faster, they appear their time slows down relative to us. But because they're in a less attractive gravitational field, they would appear to move faster relative to us. And these two effects contradict each other. And if it turns out that this effect for the ISS is actually quite a bit bigger than this effect, and it turns out to be, I think it's about a millisecond a year, as someone in the chat just mentioned, a millisecond a year slower. So the Kelly twin that went to the ISS wound up being a few milliseconds younger than his identical twin because of the time he spent on the ISS. So let me answer a few questions in this. Could this something like this be used to gain immortality and live longer theoretically? So Ryan, yes, it depends on what you mean by immortality, live longer. So by measured by your watch, the answer is no. Okay. It's by measured by somebody on the Earth, the answer is yes. So you could go to Alpha Centauri and back if you had a spaceship that could travel close to the speed of light. And when you came back, everybody has aged 40 years or 100 years. You've only aged 10 years. Okay. But you're not, I mean, you have aged 10 years, you've lived 10 years. You're not going to live on your clock to be 200 years. Now, on the Earth, it will appear that, but you haven't lived those 200 years. You've only lived 10 years. Okay. So it's not really immortality other than from the outside world. So isn't this time travel? Yes. Well, Brody, it is time travel, but all of us are time travelers. We can travel to the future as we do every microsecond. Okay. Um, and so when most people talk about time travel, they don't talk about that. And certainly this is a way for you to travel to 1,000 years in the future if you could build that. But there's another way to travel 1,000 years in the future. Just imagine that there was the technology to freeze you precisely and unfreeze you and turn you back into a live human being. That would be another way to time travel in the future. And both of those are within the realm of the physics and the engineering that we know. What isn't in the realm of anything that we know is being able to travel not forward but backward. And to travel backward, you have to give up causality. You have to give up that effects follow causes. And that's not something that I think most people are willing to give up. So chill, Brand. Okay. So space travel near black holes. So matter near a black hole will experience enormous tidal forces, meaning that one part of the object that's close to the black hole will experience a much stronger gravitational force than another part of the object. And this tidal forces where the difference between the two parts of a body are experiencing different forces and it's ripped apart. It's like the tidal forces on the Earth where you have differing gravitational force on one side of the Earth versus the other, which pulls the oceans up. but just a much more extreme version of that. Instead of just lifting the ocean up a few feet, it would rip the ocean from the surface of the Earth. Okay, that would be near a black hole. When this happens to an astronaut, we call it spaghettification. Okay. So if there is a planet close to a black hole, time would be different on the Earth. Absolutely. And in fact, there's a great movie called Interstellar where that's a major plot point. And we'll talk about Interstellar in a few minutes. And so also, not only are you spaghettified, but your time slows down. I mean, not your time, not the time on your watch, but the time that's observed from people that are far away from the black hole. And so not only do you appear to slow down, but your electromagnetic radiation slows down. So you send a light beam of your face as you head towards a black hole. Well, it starts off as, you know, your nice fuzzy, whatever color your face is. Well, but then it turns into infrared, and then it turns into radio waves as the electromagnetic radiation is stretched out. As your time slows down, the closer you get to that black hole. Okay. And that's the ratio there. Again, you're not responsible for this equation. The only equations you're responsible for are the equations that are on that equation sheet. So, yeah, let's skip this. What would you see if you were watching a strobe light falling into the black hole? Actually, go ahead and answer that, if you would, please. Somebody. It would flash slower and lower. That's exactly right, Art. And Sam, you're also right. It would get redder and redder and flash slower and slower. That's exactly right. You two have nailed it. So space travel inside black holes. What's inside a black hole? Nobody knows. Again, we predict that the mass collapses into the radius of zero and the density is infinite, but we have really no way of emulating those sorts of environments, so we really don't know. So the interior of the black holes will remain a mystery. However, we do have a couple of documentaries about it. So here's the first documentary I thought you should see.
There is an inexorable force in the cosmos where time and space converge. A place beyond man's vision, but not his reach. It is the most mysterious and awesome point in the universe, where the here and now may be forever.
On my ship, you ask.
It is unavoidable, moving through space, swallowing everything in its path. Radio waves, light.
Are you programmed to speak?
Even planets and stars. Now,
Gravity's at maximum, Dan.
my God, I think it's got us. Man is about to enter.
We got a break here too.
The black hole. A journey that begins where everything ends.
So y'all want to run out and see that documentary, right? That came out in 1979. So that's what it's like to journey into a black hole. It's listed as probably the worst major science fiction movie ever made. I just don't get me started. The next documentary I'm going to show you is a movie called Interstellar, which was co-written by a guy called Kip Thorne, who won a Nobel Prize for general relativity. And part of the reason he won the Nobel Prize was actually for this movie, because for this movie, he calculated for the first time what a black hole would actually look like, and which was verified spectacularly in 2019. Anyway, here's a trailer for that movie. I've actually met Kip Thorne. He came to UNC a year and a half ago, and I had dinner with him. He's quite the character.
The initial impetus for the project had been to say, why not examine real possibilities? Where has the world got to in terms of its thinking about gravity being able to traverse dimensions, the gravitational lensing, the effects of gravity on light around the black hole? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The thing that makes this different is that real science was woven into this film from the beginning, and woven in deeply.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's data and they created real visual representations.
What the algorithms gave us was extremely spectacular.
Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time that the depiction began with Einstein's general relativity equations from the outset.
So just keep in mind that image of the black hole that's in the movie, and then and really fuzz it, close your eyes and squint, and you'll see that picture again. That came in 2019. It was spectacular. This, for those of you that have not seen the movie, I highly recommend it, except for the ending. And those of you who've seen the movie know what I'm talking about. Everything you see in the movie is incredibly scientifically accurate. It's just stunning. What's my favorite movie? Well, of course, 2001 is the best movie ever made, and 2001 is the movie that has transcended movies and has changed more lives than any other movie. I was part of a celebration of 2001 in 1997 and in 2001 and in 2015, I believe, when we brought in myself and a bunch of other physicists to screen Interstellar. So enough about me. We talked about X-ray pulsars when we talked about neutron stars. Well, it turns out you can also have an X-ray pulsar with a black hole. And again, the same idea. You have a stellar mass black hole in around a companion star. It sucks material from that companion star. That material swirls in, and as it swirls in, it gets so hot it produces X-rays. And here is and remember the black hole is tiny, 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 tiny. Okay. And it just produces an incredibly dense plasma as the material is sucked in and produces these incredibly powerful jets of X-rays. There is one small difference. The small difference is that, and we'll talk about that in a future slide, in a neutron star X-ray pulsar, stuff actually hits the surface and produces more X-rays. Here in the black hole, there's no surface to hit. And so the material is just sucked in. But before we get there, let's talk about black hole radius and density, okay? So if you remember high school physics, density is mass over volume, okay? So the density equals the mass of an object divided by its volume. So if the volume is small, even though you keep the same mass, it becomes very dense, okay? So water is not that dense. Lead is very dense. So if you have, a kilogram of water and a kilogram of lead, the lead kilogram is going to be a lot smaller because it's a lot denser. Density equals mass over volume. And here is the Schwarzschild radius that we derived more recently. So density is equal to the mass over volume. Volume is 4/3 pi r cubed. Again, this just comes from high school physics. 4/3 pi r cubed is the volume. And there's the Schwarzschild radius. We can take that radius and plug it into the equation for density, and we wind up with this equation. It looks like a mess, but all you've done is taken the Schwarzschild radius and the definition for density and plugged it and chugged it. And what this tells us is that density of a black hole is proportional to 1 over mass squared. And that would be the density of the matter if the matter extended out to the Schwarzschild radius. But of course, we don't think it does. We think it collapses to a singularity. But this is useful. This is useful because now we're going to show you different types of black holes. So the sun, if the sun was a black hole, well, the sun has a mass of about 2 × 10⁻30 kilograms. Its Schwarzschild radius is about 3 kilometers. Like I said, about the size of Chapel Hill. Actually, Chapel Hill is a little bit bigger than that. I'll have to change that. The implied density is about 2 × 10⁻19 kilograms per meter squared. This is incredibly dense, and this is denser even than nuclear material. If the Earth was shrunk until it became a black hole, and the Earth is about 1 million times less mass, it would be 8 millimeters. Okay, so about 1 centimeter. So it's about like that. Okay, so about a centimeter. So the Earth would be really, really small, and its density is something that is frankly inconceivable. Next time we're going to talk about supermassive black holes. And the supermassive black hole at the center of our galaxy is about 1 million solar masses, about 4 million solar masses, actually. So we have 4 times 10 to the 36 kilograms. And here the radius is 1.2 times 10 to the 10th. This is about the size of the sun, okay? A little bigger than that, okay? And its density isn't really that extreme. And when I click, I'm going to fill this out with a whole bunch of other objects. So here, the Earth density, as the Earth is 5,500 kilograms per meter squared. Nuclear density is 10 to the 17th. So even the sun is beyond nuclear density. Nuclear density means all the neutrons, protons, and electrons are squeezed together into a single object, like a neutron star. And remember, atoms are mostly empty space. So here, the supermassive black holes are not terribly dense, but even stellar mass black holes are denser than any sort of material that we can conceive of. So if you take a human being has a Schwarzschild radius, and that Schwarzschild radius is 10 to the minus 25 meters, which is literally inconceivably small. However, when we get to something like the Milky Way, its Schwarzschild radius would be 1/4 of a light year, okay? What's kind of amusing is that the Schwarzschild radius of the observable universe is about the size of the observable universe. Kind of an interesting point, and its density is about the density of the universe. Okay. So amusing. By the way, if you took something the size of the moon and shrunk it down to a black hole, it would have a radius of, a fraction of a millimeter, something that you couldn't really see with the naked eye. Do black holes follow the intermediate? I'm not familiar with the intermediate axis theorem, sorry. I'll look that up after class. Oh, and here's what I was talking about. I need to move the position of the slide. In a black hole, the X-rays don't hit the surface, and so nothing happens. In a neutron star, X-rays fall down and spurt it. And sometimes X-ray pulsars from black holes and X-ray pulsars from neutron stars look very similar. And so we just look at the details of that to separate it. Another way that we separate whether it's a black hole or a neutron star is how massive the object is. If it's more than 3 solar masses, it has to be a black hole. Okay. So colliding black holes, which we postulated but had not observed until 2015. The way we observe black holes is that one of the things that Einstein predicted, and then after he made the prediction, he says that this will be completely unobservable, is that since gravity is a warping of space-time, if you move massive objects really fast, that warping moves too. In other words, if masses oscillate, it will warp the fabric of space-time itself and produce what's known as gravity waves, very much like surface waves on the surface of an ocean, okay? And so gravity waves stretch space and time like that, just like this. So if a massive object is moving very quickly and oscillating very quickly, it will warp space and time, which means that you personally are warped. You personally have your height get higher and then shorter based on something that happened 1 billion light years away. And we'll talk about that right now. So one of the ways that you can get things to move very, very quickly is if you have 2 black holes that are circling each other, okay? So here is what light would look like as it went around those circling black holes. And here is, again, we're using the 2-dimensional analogy of 2 black holes. Okay. And here's how space-time is warped based on that. So these 3 are all representations of producing that warping of space-time. And we believe that a binary black hole system is the way to produce the strongest gravitational waves. How do we detect these black waves, these gravitational waves? We detect them with an observatory known as LIGO, which was under construction for 20 years. What LIGO does is it tries to detect this shrinking and growing of space-time itself. Right now, there are 3 LIGO detectors. Well, 3 gravity waves detectors. 2 are called LIGO. One in Louisiana, one in Hartford, Washington State. Sorry about that. And the third one in Italy called Virgo. And the way it works is you send a light beam out to 2 mirrors, you bounce them back, and as those mirrors change their distance because space-time is warping, the light waves that come from those 2 mirrors interfere with each other. The waves bounce back. Those 2 light waves hit there, interfere with each other, and as the mirrors move, you will see changes in the interference pattern here on this detector right there. And this is an exact, and you can see how the light intensity goes up and down as the waves interfere constructively and destructively. This is exactly how the LIGO detectors work, except instead of something that sits on a bench, these arms are 4 kilometers long. So each arm, the LIGO detectors consist of 2 arms, each 4 kilometers long. And the end of it just is a mirror that bounces the light back, and then there's a detector at where those 2 intersect. Those mirrors move by a level of 10 to the minus 18th meters. So this is why Einstein said that gravity waves would be undetectable, because 10 to the minus 18th meter is really small. I mean, it is really small, really small. So there's 1 meter. A human hair is 1/10,000th of a meter, so about 100 microns. Divide that by 100, and we get to the wavelength of light, which is about a micron. Divide that by another 10,000, and we get to the diameter of a single atom, which is 10 to the minus 10 meters, also known as an angstrom. Okay. We go down by another factor of 100,000. Instead of the atom, we get down to the nuclear diameter, where the nucleus of the atom is. And remember, I said atoms are mostly empty space. If my house was an atom, the nucleus would be something you almost couldn't see, about the size of a grain of sand, okay, at the core. And so we go down by 10,000 to get a human hair, another 100 wavelength of light, 10,000 atomic diameter, 100,000 a nuclear diameter, and we need to go down to another 1,000 to get LIGO sensitivity. In other words, we're talking 1,000th the diameter of a proton. This is literally inconceivable. I'm still amazed that we're able to do this. And after 20 years of working on this, on September 14th, 2015, literally within hours of them turning on the system, while the system still was on test, we made the first detection. We're now up to, depending on how you count, either 40 to 100 detections of colliding neutrons, black holes. Here's what it sounds like. What you're hearing is the actual sound in real time of two black holes colliding and coalescing into a single black hole. What makes the mirror move? What makes the mirror move is that when space-time is warped, it warps everything, including the Earth, okay? So it's not that the mirror moves, it's that the distance between the detector and the move shrinks and grows as the fabric of space-time shrinks and grows. So this first detection, we detected a 36 solar mass black hole and a 29 solar mass black hole combined. And when they combine, you would expect that they would combine to create a black hole of a mass of 36 plus 29, which would be, what is 36 plus 29? Anybody? $65, that's correct. However, we measured the final mass as 62. 62. By the way, this object was 410 megaparsecs, which is about 1.2 billion light years away. I mean, this was very far away. So this object, this thing that happened 1.2 billion light years away and 1.2 billion years ago hit the Earth and made you taller and shorter on a very fast time scale. And when I said that the two masses add up to 65, but the final black hole mass was only 62, where's the missing 3 solar masses? Those missing 3 solar masses went into the creation of those gravitational waves. The conversion of 3 solar masses almost instantaneously into gravitational waves meant that it was generating more energy during that time frame than all of the energy produced by all of the stars and all of the galaxies in the entire observable universe at that point in time. This is just a mind-blowingly complex, energetic event.
Gravitational waves were predicted by Einstein almost 100 years ago.
A gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It was what we call a chirp, and it was strong.
Everybody thought it was a fluke. It was too good.
And I thought, my God, this looks like it's it.
Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect a gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from 2 black holes forming a larger black hole.
For the first time, 2 black holes
spiraling together, coalescing, merging, creating wild oscillations, a storm in the fabric of space and time.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy.
Gravitational waves carry information that you can't get from any other way. A supernova, 2 neutron stars colliding, even the Big Bang itself, the beginning of the universe, all produce gravitational waves.
This first detection by LIGO is the very first step. It's just the start of the story nature is about to tell us.
I would love to see Einstein's face. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle. settles the question for astrophysicists. Do black hole pairs form? Yep, we got one.
And they were absolutely correct. The first gravitational wave detection in 2015 was just the beginning. Like I said, they've detected, depending on how you count, 40 to 100 events. In fact, there was an event just happened last week that has made news around the world, and that's two very large black holes that we didn't think could exist, produce an even larger black hole. So here's transient. This is a catalog of other black hole collision detections, and this is like from 2017. They've stopped putting those out. Just a refresher, most of the universe we know of from electromagnetism. Electromagnetism is a very strong force. The electromagnetic waves are very easy to detect. We can see them with our eyes, but they're very easily blocked. If somebody stands in front of somebody else, we can no longer see that first person because waves are very easy to block. And what we're looking at is the surfaces of energetic bodies. So you can see the surface of your friend. You can't see inside your friend. And we construct images of the object. Now, gravity is a very weak force, and it's very hard to detect, as you saw, but it's unperturbed. It can pass through anything. So if your friend starts oscillating very quickly, I can detect the gravity waves coming from your friend, and those gravity waves come not from the surface of your friend, but from all of your friend. It's the bulk motion of dense matter. And instead of images, we often think of it as sounds, because for stellar mass black holes, these come out as oscillations in the fabric of space-time that are about the same frequency as sound, a few thousand hertz. And that's why I played that for you. Do they figure out the masses of black holes and stuff just from the properties of the gravity waves, or they collaborate with other data from other telescopes? Art, that's an incredibly great question. It turns out that you can detect the distance and the masses of the black holes just from the gravity waves themselves, just from the difference in timing of the two detectors, just the slight differences in the amplitude, in the frequency of the waves, and how fast they spin up. And normally, black hole collisions are not detectable in any other electromagnetic beam, and that was not true when we saw two neutron stars colliding, as we talked about last time, where we did detect them with electromagnetic radiation. And in fact, since the distances we calculated from the gravity waves was fairly precise, we actually used the gravity wave detections to validate the distance calculations done with electromagnetic observatories. So I'm going to skip the picture black hole. We're going to cover that next time. And so let's see, let's get to some questions. Okay, so it's pulling. And that's exactly correct. So white dwarfs and neutron stars we can observe. Black holes we can only observe by the effects they have on the universe. We really have no idea what happens inside the black hole itself. What is the final state of black holes? So the final state of the most massive stars are black holes. The region around a black hole from which no radiation can escape is called the The event horizon. That's correct. And the event horizon of a black hole is? Yeah. So the answer to this is it's measured by the Schwarzschild radius. And you remember that first graphic I showed you. There's the radius of the Schwarzschild radius defines the location of the event horizon. There's no physical surface of the hole. There's no physicality to that horizon. It's just the point of no return. It's the point where X-rays emerge. X-rays can only emerge from outside the event horizon. Nothing can actually emerge from the event horizon itself, because at the event horizon, that's the point at which the escape velocity reaches the speed of light, so nothing can escape. Defines the outer edge of the accretion disk. Again, the accretion disk has to end quite a bit away from the event horizon, because as it gets close to the event horizon, the matter just disappears. Okay. What explanation does general relativity provide for gravity? Okay. So this was a bit of a fooler of a question. The question does not ask what is true about gravity. The question asks what explanation does general relativity provide for gravity? And certainly gravity is the weakest of the four forces. And gravity is directly proportional to the mass. Gravity is inversely proportional actually to the radius squared. So this is arguably not correct. But that's not what it asked. It didn't ask which of these statements is true. It asked which of these is an explanation, is the explanation that general relativity provides. And what general relativity provides is that gravity is the warping of space-time. Okay. So the force of gravity can pull on and the answer is all of the above. Anything is, because it's not a force, it's a warping of space-time itself. Everything is deflected by that. The observed slowing of a clock in the vicinity of a black hole is a prediction of? Okay, so here's the thing. The slowing of the clock happens in both special relativity and general relativity, but for very different reasons. Again, in special relativity, your clock appears to be slower by an outside observer if you're moving fast. In general relativity, your clock appears to be slower if you're deeper in a gravitational well. In other words, you're closer to the much massive object. Okay, those are distinct and different time dilation effects. And the question asks, which effect is caused by the slowing of the clock in the vicinity of a black hole? And that's a prediction of general relativity, not special relativity. So remember, both relativities have time dilation, but one is velocity and one is how much gravitational force are you feeling? Okay. And I think this is the last question. Yes, it is. If the sun was replaced by a one solar mass black hole, what would happen? Okay, I'm going to show you the correct answer and then we'll talk about it. Okay, so there was really no consensus here. The correct answer is number one. The Earth's orbit would not change. So the Earth only cares about the gravitation, the mass of the thing that's pulling it. And the mass doesn't change. And so the Earth's orbit would continue as it did before. Nothing would change. Earth would not be pulled into the black hole. The only time you're pulled into the black hole is actually you're physically right at the event horizon itself. Other than that, you just look like any other gravitational object. And Earth would not be torn apart by tidal forces because the force of gravity is completely unchanged at the Earth. Now, of course, life would be radically changed during that. Okay, that's the end of today's lecture. I'll open it for questions, but before I do that, let me just answer some of the questions that have been popping up. Sam says, what's an example of a really super duper star? I actually don't know. I'll look that up and we'll talk about that next lecture. Will our sun ever become a black hole? Adian, I'm sorry, I don't know how to pronounce that. The answer is definitely not. Our sun is not massive enough because remember, black holes are the end result of type 2 core collapse supernovas, and those only happen with stars that are 8 solar masses and above. And for you to form a black hole from that collapse versus a neutron star, I believe the current thinking is more like 25 solar masses. So we're very far away from that. So our sun cannot become a black hole. Would we be around to see it? By the time we reach that point, it would also be causing very problematic Earth conditions. So Dan, what actually is going to happen is in 500 million years, the sun's luminosity will increase so much the Earth becomes uninhabitable. And in 5 billion years, the sun turns into a red giant and it will completely engulf the Earth. And that's the end of it. So pack your bags. I mean, the time scale isn't that amusing, but the Earth does have an expiration date. Sam asked, are these two not connected at all? If gravity is just acceleration. Yeah, so here's the thing, Sam. Special relativity is about velocity and nothing but velocity. There's no acceleration in special relativity. And that's why after Einstein developed special relativity in 1905, he spent the next 10 years trying to extend that to include acceleration, which he then realized is the same as gravity. And that the genesis of that was very difficult work. He had a lot of people helping him. He thought he was in a tight race with a guy called Hilbert to come up with a theory. And 2 years before Einstein announced his theory, he had made a critical algebraic mistake that set him back for years. And so it was fraught with peril, but eventually he was able to do it. Wouldn't the black hole gain mass over time? So yes, so black holes gain mass as they swallow stuff up. So every time you throw an astronaut into a black hole, it increase mass. And this is especially important when we're talking about supermassive black holes, which we'll be talking about next time. I wish to be spaghettified. Yeah, with a little bit of, spaghetti sauce. Yeah, I don't think so. Would you say the luminosity would be too high for habitability? Is the brightness or radiation that would cause the problems? So every object in the universe has a certain radiative balance, and we'll be talking about this when we talk about exoplanets. And so, all things being equal, it's the temperature at which the radiation coming into the surface of the planet equals the radiation that's emitted by thermal radiation leaving, and that balance must be exactly equal, or the planet's going to heat up or cool down. And so we can measure that radiative balance, and of course it modifies a bit based on clouds and things like that. And that radiative balance means that if you increase the sun's luminosity by a factor of 2, the temperature that the Earth's surface would have to be would be so hot as the oceans would evaporate and life would just be untenable here. Without the oceans, without, where parts of the surface of the Earth would be above the boiling point, the Earth would just be uninhabitable for life as we know it. Let's see. Is there any evidence behind the theory that black holes emit radiation? I'm sorry, this is going too fast. Okay. If the black hole at the center of the solar system gains mass over time, wouldn't the Earth be pulled in eventually? Kush, actually, yeah, that's correct, but it would have to gain a lot of mass. Okay. And so let's say that you had a couple of stars that slam into it and double the amount of mass there. What would happen is that the Earth would then fall in and then create an orbit that was stable, but at a much closer frequency. You're basically just shrinking the solar system if you did it, but you'd still be pretty far away from being sucked in. Is there any evidence behind the theory that black holes emit radiation of a previous universe? Joe, I had not heard that theory, so I just don't know. Why do some accretion disks produce jets while others don't? Emma, I don't know, but then nobody else does either. Doing simulations of these accretion jets is very difficult, and we've not really figured out. And we do know that very strong magnetic fields are a core part of this process. And the best guess is that for systems that have weak magnetic fields, they don't produce jets, and systems that have very strong magnetic fields produce very strong jets. Why is the photo of a black hole have such low resolution? So, Ward, imagine taking a quarter, okay? You can see a quarter. Now, if I take that quarter, and I'm in Durham, and you're in Raleigh, for example, I don't know where you are, but let's say you're in Raleigh. Could you see that quarter? I mean, it would be very difficult, almost impossible to see that quarter, okay? Now, take that quarter and move that quarter to Los Angeles. It'd be very, very difficult to see. Now take that quarter and move it to the surface of the moon, okay? Could you see the details on the face of that quarter? That is the resolution that it took to produce the image of the black hole that you're going to see next lecture, okay? When black holes merge, do they cross each other's event horizons? Why don't we just see them both eternally freeze at the instant before they're collided? So, Sam, that's an interesting question. I'm not aware that anybody has ever run a simulation of what it would actually look like with invisible light for black holes colliding. All we've done is these calculations of how they produce gravity waves. But yeah, you're correct. It would be very interesting because, so for example, let's say you take your friend and kick him out the airlock and watch him fall towards a black hole. What would happen is you would have a final image of your friend right at the event horizon, frozen in time because his time eventually slows down to nothing. But the radiation that represents your friend will then be redshifted from visible light to red light to infrared to radio waves and to microwaves and then radio waves and then down to lower frequencies. And so what would happen when, instead of throwing your friend out the airlock, you throw a black hole out the airlock and the black holes collided? Yeah, that would be an interesting simulation. I don't know. Humans wouldn't survive, that correct, as we move closer without a sun. So, you know, in the thought experiment where you were able to instantly replace the sun with a black hole, well, we would all freeze to death, you know, I mean, and that would happen over a few days, if not a few hours. So it would, you know, it would be a bad day. I don't think I'd be your friend anymore. Okay, other questions? Feel free to turn your mic on if you have a question for me. Can both massive and supermassive black holes emit gamma ray bursts of short and long durations? So we believe that it's not really the black holes that are creating these gamma ray bursts. It's colliding neutron stars, as we talked about last time. And we currently think that the short gamma ray bursts are caused by colliding neutron stars. And in fact, we have observed that. We observed that in 2017. We also think that the long gamma ray bursts, the gamma ray bursts that last over hundreds of seconds or even minutes or hours, are caused by what we now term hypernovas, which are these extremely large supernova explosions. And we further think that in the current universe, you know, stars and galaxies that are close to us can't have hypernovas. Hypernovas seem to require a pure hydrogen and helium, and not polluted with the elements from other generations. Do we get to talk about neutron star black hole collisions? Sam, I actually don't have a section on that. That actually is very new. That only happened last year, and there's still a lot of debate about that. Let me look up, see if there's a slide or two I can throw together. So what Sam is talking about is LIGO and Virgo have detected dozens of black hole collisions. They detected, I think, 2 or 3 neutron star collisions, and they claim to have detected 1 neutron star black hole collision. But I haven't heard a lot about what the results are. That there's still arguing about that, and nobody's really talking a lot about it. So my guess is they're kind of buried in the weeds, trying to figure out the details of that. Other questions? Okay, if not, I bid you all adieu. And Thursday expects to be even more exciting when we talk about the supermassive black hole at the center of our galaxy. And we talk about the picture of the black hole that was released in 2019. Thank you so much. And we'll see you in a couple of days.